Thanks, Jeff. Good morning, everyone. So Mark and I are going to take half this presentation each. I'll start us off. Just a note up front, writing a paper and giving a presentation on a topic has brought us aircraft design over the last 50 years is no daunting task. So we'll do our best to cover the bases. We tried to get a nice combination of aircraft companies, academia, and apologies up front if we don't cover your favorite aircraft and don't cover your favorite programs. And it'll be slightly Sikorsky centric because that's our basis of reference, but hopefully we cover everything. So what we'll talk about, I'll lead us off with an introduction to the Aircraft Design Committee itself, give a little overview of what the aircraft design process is, and then we'll get into the meat of the paper, which was basically three parts: design and processes that have evolved over the last 50 years, technologies that have gone into the designs, and air vehicle configuration. So the Aircraft Design Technical Committee is currently made up of 15 members. It rotates in terms of its composition from year to year. We're currently 9 members in industry, 5 in government, 2 in academia. And our general topics cover aircraft design, subsystem design, design technologies, criteria, synthesis method, and interdisciplinary considerations that get into the aircraft design. The other things that we do are student design competition coordination. This rotates from OEM to OEM over the years. This year's current competition is the Multi-Mission Modular UAS, sponsored by ARL. We also do vertical flight challenge oversight, such as the human powered helicopter competition and the current vertical flight challenge. Looking back over the last 50 years, we've had over 500 papers presented, about 10 papers per forum, actually about 2 full sessions. If you go through all of the topics and you do a keyword search, you see that the major topics of interest are, of course, design, optimization, and a lot of papers on rotor blades. Over the years, we've had papers that have covered tilt motors, high speed, compounds, and in most recent years, we're seeing more and more papers on more electric and hybrid configurations. So looking forward to the upcoming Forum 80, we have 2 full aircraft design sessions, 14 papers. 5 of them are covering VTOLs, 7 of them are related to design and optimization. We have 2 on advanced flight control. As always, we have 2 additional papers. We're going to be presenting the first place winners for the graduate and undergraduate design competition for last year's competition, which was the high-speed vertical takeoff. All right, so getting just into aircraft design. Aircraft design is really the heart of new aircraft development. There's 3 phases involved. You lead off with requirements, research, technology, market opportunities. Get into the conceptual design phase, which is really the size, weight, and power of the aircraft, the general configuration and sizing of the systems. That culminates in a conceptual design review. Depending on the level of effort, the complexity of the project, or the corporate culture that's doing the effort, it can take anywhere from 6 to 12 months and involve anywhere from 5 to a couple dozen engineers. That gets you into preliminary design, where you produce the configuration, you do your major trades, you size up your systems, and you lock in on a configuration with which to go into detailed design. System requirements review, system functional review, and preliminary design review occur during that phase. It takes anywhere from 1.5 years and can take up to a couple hundred engineers to complete. Once you get through all of your major system trades and you've frozen your OML, you go into detailed design, which takes 1 to 2 years. It can take up to 500 engineers, depending on the level of effort. And that's really where you're designing the parts that are going to be built. Right? That ends in a critical design review. Past that, you go into build, test, and delivery. Looking at an example at U.S. Army Aviation, this is a figure that we have on the paper. The first Army aircraft, the R-4 in 1943, led to the Black Hawk 35 years later. Then 30 years later, going to the UH-60M, and about 40 years later to the JMRT aircraft, which were the follow-ons to the Black Hawk. So what is aircraft design? This is a figure in the paper that we've, the Dream airplanes from Nikolai's book. You know, if you gave each functional group their say, these are the airplanes they would come up with, and they're all optimized for their particular subfunction. There was a derivative of this made sometime in the 1990s. I don't have the direct reference, but it was done by the Sikorsky Boeing command. But really, you know, the aircraft designer is the chief negotiator between all of these different groups to come to a balanced aircraft design. And I have one last chart on the design process. It's the conceptual design process. It illustrates that balance. It's really three parts. There's requirements, initialization, the aircraft synthesis itself, and then system effectiveness. So you start the process with what do you want to do, right? Payload, range, speed, mission, certification basis, technologies available, risk assessments, even export and proprietary information considerations. You come up with an initial first pass sizing, layout, and analysis of an aircraft. And then you feed that over to the configuration, definition, layout, lofting group. They come up with size, weight, and powers, layouts and lofts, areas and dimensions, and that goes into the two major integrated product teams of flight sciences and vehicle systems. So the vehicle systems group, you know, is airframe, structure, propulsions, rotors and drive. The parts of the aircraft. Flight sciences are the attributes of the aircraft, aerodynamics, aeroelastics, propulsion, mass properties, etc., all of the abilities. Out of that first iteration from the initial layout comes detailed flight sciences and system data, which goes into type performance traits and vehicle optimizations. You come out with a synthesized vehicle, you check to see, did you meet the design requirements? If you didn't, you go back and reiterate. If you did, you can then proceed into the system effectiveness for the closed vehicle. Did you feed it into your operations analysis and customer usage models? Did you meet customer requirements? If not, go back. If you did, you do a market assessment, competitive assessment. Are you viable? No, go back. Yes, go into business case and financial models to make sure that you're economically viable, financially feasible, process banks. So part one, design process tools. I like to lead off with this chart. It's one of my favorite pictures. This is the Sikorsky engineering floor, circa early 1970s. Apart from the costume, which is the white shirt, black pants, and black tie that everyone's wearing, the two major pieces of design technology in play are the rotary phone and the mechanical pencil. And that was how aircraft was done. Aircraft design was done in the early 70s. Design and layout, you know, how it evolved. You know, even through the 1980s, aircraft design was still done with hand loads and handwritten papers. In the 1980s, computer-aided design came about in the S-75, Sikorsky S-75 ACAP, Advanced Composite Aircraft Program. It's actually the first aircraft that was designed on computer-aided systems at Sikorsky. I have a reference in the paper from 1990s, an AFWEEK article showing how Comanche design was being done in computer systems, leading to 2000 mock-ups. Sizing and design synthesis. You know, we have codes from U.S. government, NASA, there's NDAR. We have references from Boeing for HEFCOM. At Sikorsky, there's been HDM, VTOL, and RDM, and of course there are other tools across other OEMs and yeah. I can speak to, you know, at Sikorsky, there's been 3 automated computer design tools that have been used over the last 50 years. It started in the late 60s, early 70s with HDM, the helicopter design model. It's Fortran based. It was the tool used throughout the 80s to do Comanche design. In the late 90s and into the early 2000s, after HDM was the vertical trending model, this took a lot of the code from HDM, added empirical trends, and really the major development was porting it to the new environment of STOL and VBA, which made it highly portable and easier for engineers to access on desktop PCs. From the early 2000s until today, we've been working with the Rotorcraft design model, which is derivative, VTM, it's still VBA based, still cell, highly portable, but major additions have been made to account for lift offset coaxes, X2s, compounds, tilt rotors, and hybrid electric aircraft. But all of these tools essentially do all the same thing. And an example of this is here's the RDM output. You know, they output a sizing output, which are the major weights and system attributes, the thing that you're sizing to, a detailed weight statement, which helps you do mass accounting, and segment by segment aircraft state descriptization of the rotorcraft power, since it's doing this design mission. You then take the sizing, you can do mission performance like payload range, radius of action, time and station, and you know, a lot of these tools today have design experiments and built-in optimizers to help get through the process that I illustrated on the previous chart. And just a quick note, you know, these tools have enabled something called multidisciplinary analysis and optimization, which is, you know, didn't really exist before the 1990s, at least in a computerized fashion. You know, tools like Model Center have evolved, and current tools like Aiden that wrapped around NDARC for the U.S. government been emerging over the last 10 to 15 years, which really brings in more comprehensive analyses into the sizing tools and can even link up analysis with CAD and Lockheed to come to a whole integrated solution. With that, I'll turn it over to Mark, who'll talk about technologies and aircraft configuration.
Okay, thank you, Mike. Yeah, so technology and aircraft configuration over the last 50 years in 15 minutes. That's easy, right? So again, I'm going to ask for the same, offer the same apology if I miss your favorite technology, or if I get something wrong, you can set me right later, but it's a very broad subject. There's a lot that's been done. So I'm going to do my best here to go through it. But I'm going to start with a framework. People talk about improving performance of aircraft, and I've always liked to be a little bit more rigorous about that, is that improvements that come from technology can come in terms of performance, which be things like speed, range, payload, altitude, things that generally require power, things that also tend to be affected by scale. But equally important is attributes, maneuverability, acoustics, downwash, safety, reliability, liabilities. Those are equally important and can make or break a mission capability for an aircraft, be it civil or military. So you like to kind of plot these two things against each other. Starting back in 1974, first flight of Black Hawk. A year later was Apache or AH-64. And over time, we've gone from large improvements in performance and large improvements in attributes. So they've really gone up both things and made the aircraft way more capable than they were back 50 years ago. What are the technologies that have done that? Well, I did my best here to kind of put technologies where they've made the most impact. So performance improvements very much by propulsion, and it's kind of the size of the bubble there is the kind of the impact it had. So propulsion systems in terms of transmissions, their power to weight ratios, and particularly engines, they've just gotten much, much better over time. Structures and composites, a lot of weight reduction, which goes into performance, gives you more capability for the amount of power and the size of the aircraft. Heads, rotor heads and blades, now you're getting into both attributes and performance, right? Better figures of merit, better L/Ds, but acoustic improvements, ballistic tolerance improvements, icing, de-icing capability. So that's one that kind of crosses into both. And then we get more to the attribute side. We'll start with fly-by-wire. We'll be talking about that very much in the attributes of the aircraft. We're trying to get away from CFIT, carefree handling, loads reduction capability through model following type systems. And building on that is autonomy, which very much gets into hopefully much improved safety of the aircraft, probably more accurate flight profiles, and that's kind of why it's overlapped there. Electric propulsion, it's coming. We're going to see where it goes, but the simplicity of it, hopefully, should be much lower cost. Again, more of an attributes performance thing. So I just wanted to give you a framework there, a way to think about it in the future, about when people talk about technology, kind of where does it fall into the spectrum of improvements. So we're going to go through each one of these technology areas, and we'll start with propulsion systems. So, constantly improving performance, and a lot of that's just because pressure and temperature ratios increase, right? They're just packing more and more energy with the same amount of mass flow coming through. And here's some data I pulled out of a paper looking at the power, horsepower per pound versus size. Now, engine performance is very size dependent, so you got to be careful when you're comparing power to weight ratios or SFC. You got to know the class you're in, so that's why I've got it plotted versus power here. And you can see the power weight ratio is getting much better with size, something I showed you yesterday, but you can see the band, and the lower band is the mid 70s and up here in the 2020s. And those percentages are very large. And so that's been a big improvement in what we can do with an aircraft and how much power we can put on board. And of course, with the more power, you tend to get more performance. Now, it doesn't cost us near as much as it used to. Here's an example, T-700, 1974. That's a picture of the first, or one of the very first T-700s at the National Aerospace Museum. 1,560 horsepower, 423 pounds. It was designed for FOD tolerance, ballistic tolerance, had a modular design, and had improved maintenance, which is a big jump for the time from the engines that were being built. Purpose built for the military, for the Army. LH Tech, T-800, 2001. So, many years later, same horsepower, look at the weight, 330 pounds, much lower, designed for a very high power to weight ratio. And even better maintenance, what they call two-level maintenance. There's a whole thing about reduced tools. I remember at Sikorsky, they had a picture of all the tools you're allowed to use, and that was on the board only that big. So they're really going after the maintenance and then the beginning of electronic record keeping. So that's just one example of many engines across the industry that have gotten better and better over time. So electric propulsion, here's a picture of the Sikorsky Firefly. This is back in 2010. Sikorsky was really interested in seeing how electric propulsion would kind of work on an aircraft. And this is a great picture because it shows all of the internal combustion engine, Lycoming engine, pulled out of that aircraft and all the other stuff that goes around it. Fuel tank, wires, exhaust, cooling fan, so forth and so on. And it's replaced by what's on the right-hand side here. That silver canister is the motor. And all the other stuff you see, the transmission, which is a belt transmission. So the simplicity that the electric propulsion offers is looking pretty good. But we're still in its infancy. We've got to work on these motors for good aircraft applications, and we'll see where that leads. But the big thing about electric propulsion, of course, is the motor power density and the battery cell energy density. So here's some plots. Year on the bottom, kilowatts per kilogram in terms of the motor on the left, and we got battery cell on the right. And it's just, it's one of these exponential rise curves. And that's really what's gone from 2010 to barely being able to fly to what we have today with things on the verge of certification. The tricky thing here, though, is if you look at the history of technology, you quite often see these low rates of increase and these large rates of increase. The question is, and this is where we are, do they keep going or do they fall over? And that's called an S-curve. This is very typical of technology development. We're at that point right now. These batteries and motors, their power and energy densities are going up. And then at what rate is it going to come over? Well, we'll see. It's kind of the big guess. And quite often those are taken over by another S-curve and with some other big battery chemistry, some other way of doing motors. So we'll see where it goes. Composites, right? Big thing certainly in VTOL, right? Waste's the enemy. Also it's for aircraft, particularly for VTOL because we're challenged. But this is a very interesting plot in that for year of first flight and the percent of composite materials as a percent of total structure weight. And you can see a lot of aircraft, pretty familiar with them. That'd be good just to cover some of highlight some of the more outstanding ones there. Let's start with the S-76. That's a picture of the first 76, 1977. If you're up on your aircraft configuration, notice the tail is different on that aircraft, at a stable area. But that aircraft was designed to be very slick, very efficient cruise, 155 knots. And really no other civil helicopter can really reach that on a, regular 155-knot cruise. Had to be very clean. That means, swoopy clean lines. Composites were good for that. So Sikorsky invested in that in the early days. Rotor systems also were picking up a lot of composites. There, you can see the percentages here. We went from, less than 50% to over 67% composites and rotor systems. And we'll talk about rotor systems coming up. And very great fatigue properties, lightweight, bringing the fibers the way you want to pick up the loads in particular directions. The two ones up there in the late 80s, the 8-cap programs were really, really outstanding programs. Army said, build us a helicopter as much composite as you possibly can. Let's see what happens. So both Sikorsky and Bell had contracts. They used some of their civil variants as civil aircraft and turned into composite aircraft. And look at the percentages way up there. Tremendous learning experience and fed into the LHX program, the Canadian program in particular. V-22, really dependent on composites. World mode flutter is, the thing you're really worried about, and the weight, well, composites are wonderful because you can orient the fibers, very stiff. It's all about stiffness to get the frequencies where you want them. You get world mode flutter, and of course, being a high-speed VTOL, weight's even more of a challenge. So composites played a very, very big role in making the V-22 come to be. And today, H-160, swoopy, clean lines, lots of composite structure. I believe they got more automated manufacturing processes to keep the cost down, so it's just ever increasing. So rotor blades. So this is format here. You'll see this Gen 1, 2, 3, and 4. And the aspects of the blades are design, performance, and manufacturing. So again, a framework to think about how the evolution of blades have gone. The generation thing is something Sikorsky used. There's probably similar types of ways we categorize them in technology that have been other companies. But basically, design comes down to airfoil types, twist distribution, and design. You get the aerodynamic performance up. And you can see twist has gone from linear and low all the way up to these highly nonlinear blades in terms of twist to get the performance up. Airfoils have gone from symmetric to cambered and complex shaped and tailored shapes, right? So all our CFD codes have been allowed to enable us to do that. Performance, bigger merit, right? Big important thing for takeoff, below 0.6s or up to 0.8 in neighborhood, depending on the aircraft. So a lot of the first three rows are giving us a performance in the fourth one, and then manufacturing. We've gone from aluminum all the way up to fancy composites, automated fiber replacement, and so again, a place where composites are coming in. Some noticeable pictures, examples. Here's the BB360. They're trying to get 200 knots out of the aircraft. Their approach was to taper the tip. So you get rid of the advancing tip Mach effects or the high torque effects, whereas Westland said, well, we're going to put more tip out there to mitigate retreating blade stall. So of course, edgewise rotor, you're fighting one thing on one side, one on the other. You can kind of decide which one you want to go after. So two different approaches, but both very different plane forms that were enabled by the design, performance, and manufacturing. Prop rotors, right? V-22 prop rotor, very different animal than a regular edgewise rotor. Again, enabled by composites, high twist, non-linear twist, very specific airfoils for the tilt rotor application. And again, so this is a very important step in the technology of rotor systems. Rigid rotors, Sikorsky's working on their X2 concepts. So now you've got a very rigid rotor, primarily designed on stiffness, fancy tip shapes, swoopy plateform, a lot of change in cross sections down the way. And a similar edgewise rotor, the blue edge blade, look at that plane form, look at the leading edge sweep and the aft sweep, really fancy, going after noise reduction, DVI noise reduction, all enabled by the technologies of composites, aerodynamics, on the left. Let's talk about rotor heads. I've been looking at rotor heads as part of my job. I'm amazed at how many ways we can attach rotor blades to an aircraft. So I'm going to cover 6 here. I'm probably going to miss some other ones that are pretty important, but we'll start here. We started with wet heads, hinges, right? ST1 back in the 60s. Well, and then titanium became more available. We learned more about it. And this head is particularly important, I always thought, because it's very low drag, and it was a semi-rigid head in the Western lengths. They had very, very flat, flexible members, and a lot of work in the metallurgy or looking at the fatigue spectrum, the rotor system, and really pretty clever design. Then the other thing I always thought was extremely clever was elastic guard bearings. When I first came to Sikorsky, I said, well, what's the rotor head? I don't see any hinges on there. He said, we use something called elastomerics. You go, what that? Well, you take steel and rubber in layers and you glue them together, and that's your bearing. I said, really? Glue and rubber? Yeah, it takes all 6 degrees of freedom. You've got freedom in pitch, you've got freedom in flat, freedom in lag, but it holds 100,000 pounds of centrifugal load, and it can take the shears and lift and drag. That's pretty amazing. It's really quite compact. So elastomerics have been, really came to be back in, about 50 years ago, and they're still used today in snuggers and all over the place. So pretty amazing. But then composites, right? We're getting better at composites. All the analysis we can do, the materials are getting better, materials are getting certified. So Sikorsky came up with flex beam tail rotor, where you take 2 long paddles that are flexible, literally put them together like this or slightly out of plane, and they're flexible enough to take pitch, but they're very simple. No drag, tail rotors have got their own drag. So that was a pretty interesting piece of work. But then Bell took it a step farther. They said, well, let's do something similar, put it on a full-size aircraft. So the 680 rotor system, again, 4-bladed rotor, flexible beams, cuffs that come around the outside in this case. Low parts count, simple, and worked out pretty well. So Sikorsky said, well, we're going to go after composites, but we need 5 blades, so you can't use a cruciform anymore. So they had to come out of a way with making a hub. And what looks simple, but is really not that simple, is all the bolts, right? You've got to bolt these flex beams onto a metal part. And so a lot of work went into how do you bolt composites together under high loads. And with that, they're able to do that, and they came up with the Comanche rotor system with a fairly good hinge offset, very rigid, semi-rigid rotor with good agility. And then tilt rotors too, different animal, right? You don't want something super stiff. In particular, you don't want any of this kinematic feedback where the rotor flaps and you put in little accelerations or decelerations in the rotational rate of the rotor system. So I came up with things called the drag link rotor. And just really fundamental to making a tilt rotor work and getting up those flutter speeds up to the speeds you need to match the performance you want in the aircraft. So fly-by-wire, avionics, cockpit systems, of course, we've, from 1974 to today, just tremendous advances, and you could spend hours talking about this. But this is kind of a neat plot in that you're starting with, simple autopilots, and you're working your way up all the way to full autonomy, right? So you can see the pictures there, various aircraft. Some notable aircraft, the Comanche needed to be fly-by-wire for various reasons. How do you test that? So Sikorsky grafted on a cockpit on the front of S-76, full fly-by-wire controls, 2 pilots in the back with mechanical. We were able to test the whole thing and fly various pilots, very effective. Eventually, the Sikorsky all fly-by-wire MU aircraft was the first time we took a Black Hawk and did completely fly-by-wire. And then we're looking at the Relentless, which is supposed to be the first full fly-by-wire civil rotorcraft. So it's really gone, quite, a lot to learn. A lot of progress, I should say. On cockpits, we started with everything from steam gauges. You probably heard that term. I remember when I first got to Sikorsky and somebody explained the cockpit to me, they said, we've got these brand new things called strip gauges. We're going to get rid of that round oil gauge. We're going to have strip gauges. They go up and down. The pilots love it. It saves space. They go, oh, that's pretty cool. Well, look where we are today. You can see all the way down from semi-glass to full glass. And then the Valor's showing a complete panel of just all glass, right? It's completely configurable. So autonomy is really built on top of fly-by-wire, right? So you'll see that topic at the beginning there. The aircraft, to be autonomous, aircraft needs to learn how to aviate, navigate, and communicate. And if you're a pilot, you will recognize that. Taking the pilot out, so you got to take those 3 things a pilot fundamentally do is put that in the aircraft. So what's made that happen? Well, increased computational power. You got to have the brains to take in all the inputs and figure out what to do autonomously, not actually fly the aircraft. And that information came from miniaturized navigation sensors, AHRs, all that stuff that, the seat of the pants stuff had to replicate that electronically and feed that into the computational power that's going on at the airport. And then you got to communicate. You can't just send it out there and hope it comes back, right? So, communications bandwidth, the security of the communication is important as well. So those 3 things have really run in parallel. It's gotten better and better and better. And you can see the some of the more important aircraft on the bottom. The one thing I added here was certification precedents. Taking the pilot out, somebody had a really good comment about the WISC autonomous aircraft. Who's piloting command, right? So we've got some serious certification precedents to set if we start having these autonomous aircraft, both in terms of military and civil. Okay, so I'm going to wrap up here. So I got to get configurations here. So I stole this chart from my previous one, but this is here for a different reason. Is that the architecture is really good for helicopters and scaling, but because the architecture is the same, you've got the same configuration limitations and core attributes that helicopters have got. So what have we done? Well, the quest for improved VTOL performance and attributes, right? So there's the infamous wheel of misfortune. Most of those aircraft didn't make it to production. Another way of looking at it is on the right, where there's a matrix where you have everything from rotors to turbojet, and what is your tilting to get the forward thrust or adding to the forward thrust. Well, everything we've done is in the shaded area that's not helicopter. It's all in the quest for improved performance and attributes. So what I did here is I took all the legacy aircraft and other ones that are not, in addition to the wheel there, and I categorized them. And it's kind of interesting to see where they all land. Too many helicopters to list in the upper left-hand corner, but I'm sure you know many of them. Tilt rotors are coming along. We started the XV-15, even after the XV-3, and now we've got 4 aircraft either in production or going to be headed for production. X2 technology, looking at a compound helicopter, getting up there in 200 plus knot neighborhood to push the edgewise flight capability. The Harrier is a remarkable aircraft for its time. The engine, a lot of work on the engine. They wrapped around a relatively simple control system and actually got a production vehicle out there flying. And of course, the F-35 has pushed the state-of-the-art much farther now with a whole different architecture and propulsion, but much better handling qualities on the aircraft. And coming in the future, you gotta look at the future. Bell folding tilt rotor, pretty interesting. I remember looking at that back in the late 80s. There was some work done on it. Maybe it's time finally. And Aurora's out there looking at some ducted fan devices. So that's kind of what's been happening and maybe where we're going. But then we've got eVTOL. So looked at all the eVTOLs out there and a couple of these other microjets, and I put them in the same matrix. And look how the topography is very different. Almost all of them are in a propeller column. Some notable ones is I believe this was the first recognized official electric helicopter back in 2009. R-44 is probably the only serious all-helicopter electrical development working on port certification, I think. We have personal VTOL electric vehicles, right? The Blackfly, there's one downstairs in Hexa. And of course, we have Beta, Joby, and others that are Wisk and Archer all pushing towards the urban air mobility stuff. Again, most all propeller type aircraft. And then these two, I'm going to forget, it's not all just eVTOL. These microjets are really amazing. If you go online, look at the flyboard and these gravity guys, these are really quite amazing, and they're all kinesthetically controlled. And so it's kind of interesting to see where they're going to end up. So what I did here is I just did a mapping update. Here's the left-hand side is the legacy VTOL aircraft. You can see the topography. The new eVTOL and the microjets, you see they're almost all lined up under propeller. We're all trying to go for that direct drive, almost all of them. And almost all of them are also that constant fixed pitch propeller. Hence some of the reasoning for the presentation that we listed, right? So another way of looking at it and kind of getting a framework. So I'm going to wrap it up here with one more chart, probably running late. It is right here. So we live in an interesting time, right? Similar early air transport. So back in 1920s, airlines were just starting, and I found this cool poster. It was Imperial Airways, which is no longer around. And look at the people, very nicely dressed. It was expensive, but it was an adventure. It was really something. And it was the beginning of air transport, and all the rules and regulations and learning were coming. Well, you've got electric propulsion aircraft, much quieter, hopefully much simpler, looking to get the cost down and maybe really get into the urban environment. And we've got all these regulations and unknowns and companies that are going to go bust and companies that are going to go, like gangbusters. And so it's an interesting time, a little bit harking back to the early days. So good thing we're here to watch it and help it come along. And I'll wrap it up here, and I think we'll take any questions you got.